So the hydration mechanism is really similar to hydrohalogenation, and we also see the more substituted product formed because the more substituted carbocation will form. So in the first step, the two electrons in the pi bond will reach out and grab that proton, and the proton will be bonded to the less substituted position so that the carbocation ends up being on the more substituted position. We wind up with our carbocation intermediate. Nucleophile then comes in and forms a bond with the carbocation. We wind up with our oxonium ion is what that's called. It's a positively charged alcohol intermediate. And so this is acidic, and a base, most common base around is going to be water. There's probably a lot of water around, and so you can grab that proton to give the final product. So you might recognize this reaction. It's the reverse of dehydration. And you can favor the addition reaction, which is forward as written here, or the elimination, which is the dehydration, the reverse reaction. And so looking at the thermodynamics of this, if we go forward, we are going to have a negative enthalpy. In other words, that's favorable because we're making two sigma bonds and breaking one pi bond. And so that's that has a negative delta H. But delta S is also negative because we're going from two reactants to one product. So in order to favor hydration, in other words, the addition reaction, the forward reaction, we want to have a really low temperature because delta G equals delta H minus T delta S, and delta H is favorable, but delta S isn't. And so if temperature is really low, then the delta S kind of goes away. And delta H will control the reaction and it will be spontaneous. You could also add in one way or another a bunch of water, and by Le Chatelier's principle, that will shift the equilibrium to the products. Essentially, you do the reverse to get the reverse reaction. High temperature will make the delta S really important in that delta G reaction, and so that will push this reaction back the other way. And you could also remove one of these products. You could take water out, or you could distill the cyclohexene out. And if you remove those, then the reaction will shift to the left. So that's how you can control whether you get an addition or whether you have an elimination. All right, so so we've talked about carbocations, and that might have kind of a red flag for you because, of course, if you have a carbocation, you're going to have a rearrangement. And so here, let's say that we start with our alkene, and we use that sulfuric acid. We're going to get that secondary carbocation being formed. The proton will bond to the primary position. So secondary will be the carbocation. But this can then rearrange, and one of these methyl groups, you can get a methyl shift, and when you do that, you wind up with the positive charge on a tertiary carbocation, so that's favorable. And then you can have that water come in, forming the oxonium ion, and deprotonate it to give you the final alcohol. So that's a rearranged product. If you don't want rearrangement, an alternative is to use something like oxymercuration, demercuration. Really, these days, we don't use a lot of mercury. There's other ways of doing this. But most texts still just call it oxymercuration, demercuration. And so the idea here is that you want to avoid actually forming a full carbocation. And so if you add a metal, what happens is the metal kind of sits on the double bond, and we see this happening all the time. It's kind of like when we have a hydride shift, and that hydride is kind of just sitting right in the middle of the bond. It's just the most stable position for it, kind of right in the middle there, and that's what happens with the mercury. The molecule down here isn't the same as the one up here. It's just kind of showing you what that mercury is doing. It's sitting down here. And that means that the positive charge will form at the more substituted position, at least to some degree, but it won't be a full carbocation. It'll be just a partial positive charge. And so then the nucleophile can come in, the water can come in and react with that partial positive charge right here without ever having a carbocation rearrangement. So whenever you see mercury, just know that you're doing some sort of an addition reaction, and you're not going to get a carbocation rearrangement with it.